All right, thanks so much for the introduction and thanks for the invitation. Welcome to the workshop. So I'm going to talk about Amplituhedra and origami, and I'm going to start with the physics, and then at some point I'm going to switch to origami. So let's say you have a bunch of particles. You have n particles in the 3+1 dimensional space-time, and assume that all the momenta are incoming. So the momenta live in this space, and then because of momentum conservation, the sum of momenta is 0. And each momentum you're going to assume is null, right? So the particles are like gluons in the n equals 4 super Yang-Mills theory. And so the 4 coordinates of the momenta have to satisfy that this sum is 0. Okay? And then I'm going to do something slightly weird. Namely, I'm going to switch to the 2+2 dimensional space-time. So the space is 2-dimensional, time is 2-dimensional, and there's a plus here. So this may seem a little weird to you. I don't know. It's 2-dimensional time may be counterintuitive, but I have a screenshot from a physics textbook, which tells you that it may not seem physical to take these. I mean, basically, if you work over complex numbers, then any 2 signatures are the same. So yeah, it may not seem physical, but it's a very, very, very useful strategy. So 3 times, very useful. And they even recommend switching to the signature with 2, 2, because then some kind of angle and square spinors become independent. So that's exactly what we're going to do. So I have these particle momenta, and because the first 2 coordinates are with the plus and the next 2 are with the minus, I'm going to think of them as just a pair of complex numbers. Okay? So each particle momentum is a pair of complex numbers of the same absolute value. That's the input of my amplitude, and then the output is basically the amplitude is the function of these particle momenta, which tells you, or maybe some other quantum numbers like helicities, and it tells you the sort of the probability of the particles interacting in some way. So, you know, with some probability, they're either going to pass through each other, or they're going to explode, or something else is going to happen. And yeah, so that's the end of the physics part. And now I'm going to switch to origami. So here's a picture. This is the main object of the talk. It's the origami crease pattern. So by definition, it's a kind of cell complex in the plane. So each face is a convex polygon. They're colored black and white in a bipartite way. And the main kind of condition here is the angle condition. So at each vertex, at each interior vertex, there's a bunch of white and black faces around that vertex. And so the sum of white faces, of white angles, has to be equal to pi and has to be equal to the sum of black angles. Right, so you look at any other interior vertex, and you can check that the sum of white angles equals the sum of black angles. And that's kind of precisely the condition that is going to guarantee that you can fold this piece of paper into some kind of flat origami shape. Okay? If you have some experience with origami, so basically, rigorously speaking, there's this origami map, which is just by definition, it's an isometry on each face of this crease pattern, which flips the orientation of all black faces and keeps the orientation of all white faces. So if you apply the origami map to this picture, what are you going to get? By the way, feel free to stop me at any point with questions or ideas. Again? Okay, I can't hear the audience. Okay, that's fine. All right, the answer is a bird. In this case, you're going to get a, was that the guess or? All right, anyways, there's a one-way communication channel. So you get a bird. And so it's going to be black on one side and white on the other side, because all the black faces, the orientation was flipped. All the white faces, the orientation is the same. Yeah, you just fold this piece of paper along. If you unfold the bird, these are going to be precisely the creases. And I don't care if they are like this or like this. Like, usually people in origami care about like whether you should fold it this way or this way, but I'm not going to care about this. All right. So and notice that in this picture, every line segment like this thing here. And basically, I'm going to focus on the ones on the boundary, but any line segment it's a vector in the plane, right? It's a complex number, and then its image under the origami map. So for example, this boundary line segment corresponds to this line segment here. Its image is also a vector in the plane, and they have the same length. So these are going to be my particle momenta. These are four-dimensional vectors satisfying this condition. So if you go around the boundary of the polygon, so first of all, if you take the first two line segments, they correspond to the same line segment here because the sum of black equals the sum of white at this boundary vertex. And then so you just keep going around the boundary. And yeah, so for example, to go from here to here, the white angle is smaller than the black angle. So once you fold, you're going to get a different line segment, and etc. So basically, you go around the boundary, and that's my kind of input of the amplitude, right? Is all of the boundary of the original crease pattern together with the skeleton, the red skeleton of the bird. Okay.
Does it satisfy the momentum conservation?
Yes. Well, I mean, yeah, that's going to be, I guess, a lemma or something like this. Okay, so the preview of the main theorem of this talk is that the amplitude can be written as an integral over, so it's a function. The amplitude is a function of these particle momenta, which fix the boundary of the origami crease pattern. And so the claim is that you can, if you look for all possible ways to fill this in using, so that the angle condition is satisfied, then you take the integral, you get the amplitude. All right. Any questions so far? Okay. So yeah, that's the main result. Boom, I guess. And yeah, now I'm going to try to actually formulate the main result rigorously. So far, this was sort of very hand-wavy. And to do this rigorously, I need to introduce a little bit more notation, which is familiar to all the physicists and none of the mathematicians, maybe. So that's the Spinor-Helicity formalism. You have a pair of complex numbers of the same absolute value, and you want to factorize them. So you take the first complex number, and you write it as a product of lambda times lambda tilde, where lambda and lambda tilde are some pair of complex numbers, just any pair of complex numbers. So you write the first one as lambda lambda tilde, the second one as the complex conjugate of lambda times lambda tilde. And these two products are of the same absolute value. So there is some freedom. You can convince yourself that you can always factorize in this way, but there is some freedom. Namely, you can rescale the first guy by t, some kind of real number t, and then divide the other lambda tilde by the same number t. That's called the little group action, but that's the only freedom you have. Okay. So another way to encode this particle moment is just specify these complex numbers lambda and lambda tilde for each I. And instead of thinking them as complex numbers, I'm going to just forget that and think about them as just vectors in the plane. So if I group all the lambda together, so lambda 1 through lambda n, they're going to form a 2 by n matrix. And similarly, the lambda tildes are also going to form a 2 by n matrix. So what I'm going to do is I'm going to take the row span of each matrix. So I'm going to get a pair of two-dimensional planes in the real n-dimensional space. And that's called the Grassmannian. So this is the Grassmannian of two planes inside the n. Sure.
How in the second row lambda I bar is equal to lambda I?
Lambda I bar is equal to, I mean, yeah. If you to run this construction, you have to choose particular matrix representatives, right? So now, if I only care about the row spans, that corresponds to kind of modding out by Lorentz transformations. All right. So yeah, so your input is now a pair of two-dimensional planes, and then the momentum conservation, if you write it in this way, is just gonna say that the two planes have to be orthogonal to each other. If you really go through this construction, yeah, then just your input is a pair of perpendicular two-dimensional planes in Rn. So yeah, and the main kind of subregion, this is called the space of all such pairs of two planes is called the kinematic space. And so I wonder if I I shouldn't write on the blackboard, or should I? Is there? Okay. There is chalk? Yeah. So let me know if you don't see it, but let me at least try. So the positive kinematic space is the set of all pairs of perpendicular two planes.
You don't need to erase anything because everything will be perfect, but just in case.
Okay, thank you. Yeah, everything is going to be perfect. So lambda, lambda tilde belongs to the Grassmannian 2n. Can you see? Can people in the back see this? Okay. And the conditions are some kind of brackets have to be positive for all I from 1 up to n. And also, so the winding numbers. Winding number of lambda has to be k minus 1 times pi. And the winding number of lambda tilde has to be k plus 1 times pi. Okay. Oh yeah, you can't really see. Let me do this.
So I have one two-dimensional vector after another. There's one around and some.
Yeah, there's some cyclic structure. Yes. Yeah. Originally for the particles, you don't think there's cyclic structure, but we choose some kind of color ordering or whatever the keyword. All right. So let me explain what goes into this definition. So first of all, the brackets are just the 2x2 determinants of lambda and lambda tilde. And this is so all these consecutive minors have to be positive, and this goes from I from 1 up to n, where you have n plus 1 bigger than 0. So lambda n plus 1 by definition is equal to lambda 1 up to a sign. And the sign which depends on the parity of k. K, yeah, I guess. So if you fix two integers just in advance, k between 2 and n minus 2. And it's the number of particles of negative helicity. All right, so you've got this called the twisted cyclic symmetry. And finally, the winding number is, so each lambda I is a vector in the plane. And so you just measure how much they turn in the counterclockwise direction around the origin. Here's some examples. So here's a lambda with a winding number pi. So we go from lambda 1 to lambda 2. The bracket is going to be positive, so it's going to be counterclockwise. And so you just go from lambda 1, 2, 3, 4, 5, 6, and then lambda 7 is minus lambda 1. So your winding number is pi. And here is another example where the winding number is 2 pi. Here it's 3 pi. So we go lambda 1, lambda 2, 3, 4, 5, 6, 7. I made the turn and a half, so it's 3 pi. Is clear? So the thing on the left, lambda lambda tilde, is a point in the positive kinematic space for k equals to 2 and n equals to 6. And on the right, it's k equals 3, n equals 6. So the parity is different. And that's why here lambda 1 equal to lambda 7. Here it's opposite of lambda 7. All right. So that's kind of this positive kinematic space is one main ingredient of the main result. And the other main ingredient is the positive Grassmannian, or the totally non-negative Grassmannian. So I'm assuming many people have seen this, but let me just say, so the usual Grassmannian is the set of k-planes inside the real n-dimensional space. Just all k-planes through the origin. And you can think of each k-plane as a k by n matrix. So it's the row span of a k by n matrix. And then the condition for the totally non-negative Grassmannian is that these all maximal minors of the matrix have to be non-negative. Okay, so there is like n choose k maximal minors. They all have to be non-negative, and that's the totally non-negative Grassmannian, which was introduced by Postnikov and separately by Lustig in different language. Yeah, so these are the two ingredients, and then here's the main result. The main result is that there is a simple bijection between origami crease patterns that I defined on the first slide, and triples lambda inside of C inside of lambda tilde perp, where lambda and lambda tilde belong to the positive kinematic space. So they satisfy the winding number conditions and these positivity conditions here. And then C is any totally non-negative K-plane that has to fit in between lambda and lambda tilde perp. And the little asterisk here means that it's not quite a bijection. You know, there is some natural group action on the two sides. And so if you mod out by that group, by those actions, then you get an honest bijection. So for example, as I mentioned, if you act by row operations in lambda, lambda tilde, that corresponds to kind of Lorentz transformations. And I also mentioned the little group action, which scales the columns of lambda and lambda tilde simultaneously. And then you can shift and rotate the origami crease pattern. And you can also apply some kind of square moves for people familiar with Playbig graphs, planar bipartite graphs. Yeah, I'm assuming all the graphs are reduced in the sense of Postnikov, and then I mod out by square moves because they don't change the triple. Yeah, so you can forget what that's like a legal disclaimer. You can forget what I just said, and basically you've got these triples on the one side and origami crease patterns on the other, and so if you just focus on lambda, lambda tilde, these are the particle momenta. So they determine the four-dimensional boundary of the origami crease pattern. So the original boundary polygon and what happens after you fold the boundary polygon. And C determines everything else, what's happening inside the origami crease pattern. And the amplitude is basically an integral. You know, it's well known from this physics book that it's an integral, but it's a function of lambda, lambda tilde, right, the particle momenta. And it can be written as an integral over all totally non-negative C, which fit in between lambda and lambda tilde. And I have another screenshot from this physics textbook. So this thing on the left is some kind of on-shell function, which, you know, closely related to the amplitude or literally the amplitude, depending on which formula you take. And then this thing here is the canonical form. And this is a pair of delta functions, which together fix lambda to be inside of C, and then C to be perpendicular to lambda tilde. Okay, so.
Is a single origami pattern then the image of some particular 2n minus 4 dimensional cell in the positive Rachmanian?
Yeah, it doesn't have to be 2n minus 4, just any positroid cell. Yeah, yeah, yes. All right. So that's the main result. And this theorem is kind of, it takes some work to prove. It's like maybe 40 pages to prove. Like it takes a while. But once you prove it, you get a bunch of results, kind of not for free, but easily. You can easily obtain some results. And in particular, one result that I'm going to explain is that the BCFW triangulation conjecture is true in the momentum space, right? In this positive kinematic space. So the claim is that the BCFW cells are going to triangulate what is called the Mandelstam positive region of the positive kinematic space. And I'm going to explain all the words here in a little bit. Any questions? This is the main result of the talk.
This Mandelstam positivity is not yet show up.
Yeah. So far, there is no Mandelstam positivity. Any other questions? All right. So yeah, let me try to explain the BCFW stuff in a bit more detail. First of all, here's a simple question about origami for the people that have some experience with origami. So let's say you take a piece of paper like this, and you pick two vertices. Maybe I'm going to pick them on the boundary. So you pick two boundary vertices, U and V, and then you fold the paper, so you get this little bird. And what I'm going to do is I'm going to measure the distance. I'm going to measure the distance between the original 2 points, and then the question is it always going to be bigger than or equal than the distance between the origami folded points? It's a question. Just yell it out.
Yes.
Yes. Who thinks yes? Raise your hand. Okay. Who thinks no? 1, 2. Okay, 2 people. Nice. Yeah, the correct answer is no. But it is yes for this particular piece of paper. So if your piece of paper was convex, then it's going to contain the line segment entirely. Like you can picture actually drawing this line segment with a pen. And then if you fold the paper, the distance is only going to decrease. That's very easy. But what if your origami crease pattern is not convex? So imagine you have some kind of piece of paper that's not exactly rectangular, and then like this is still a valid crease, origami crease pattern. You can check that at each interior vertex, the sum of white angles is pi, and the sum of black angles is pi. And yet, so the distance between these 2 points is going to slightly increase if you origami fold this piece of paper. This is not going to be anything beautiful like the bird. It's just kind of some kind of mess. But these 2 points are going to, it slightly increases. And an origami crease pattern can even become a little bit self-intersecting. So here's a different origami crease pattern where it's still true that at each angle, at each vertex, the sum of angles is pi for white and black faces. But you see that there is a little bit of a self-intersection. So it's still kind of immersed. So for me, it's going to be valid. But and this is not going to, when Mandelstam variables are positive, this is never going to happen. So you can forget about this. But I'm just showing you that in the paper, I have to deal with these self-intersections in some way. OK. So that's the origami question. Now let me switch to physics. So in physics, people study these Mandelstam variables, planar Mandelstam variables, which by definition, so it's a function of particle momenta, which is obtained by you take a bunch of cyclically consecutive momenta, take the sum, and take the squared norm in the Minkowski space. And these functions appear in the denominators of the scattering amplitude. So they are very important. You can kind of think of them as, if you think about positive geometries a lot, then you want some kind of positive region to have boundaries where the denominators vanish. Okay? So you want the singularities of your amplitude to correspond to walls, like the different boundaries of your region. And so in that case, in that sense, it's natural to ask that these Mandelstam variables have to be positive. And so the connection is that, I mean, in retrospect, it's kind of obvious because I already told you what the norm is, right? This sum is a pair of complex numbers, not necessarily of the same length. And so the squared norm is the difference between the length of one and the length of the other. And the two complex numbers here are going to be the difference between two boundary points of the origami crease pattern and their origami images. So positivity of Mandelstam variables precisely corresponds to situations where this inequality is true for all pairs of boundary points. And in general, it's false. So and the physicists also know that sometimes the Mandelstam variables become negative. That has been their problem as well. So let me just define I'm going to define the subregion of this space, the Mandelstam positive subregion is the subset lambda lambda tilde inside the positive kinematic space. And then the condition is that all Mandelstam variables have to be strictly positive for all I and j. And so the BCFW result is that this region is what gets triangulated by BCFW cells. So there is this parallel story for the momentum twister amplituhedron, which is the usual amplituhedron, which was introduced by Nima and Yara 10 years ago. And so they conjectured that the BCFW cells triangulate the shifted BCFW cells triangulate this amplituhedron. And then this conjecture was proven in these papers pretty recently. But as far as I know, there is no direct implication between these two theorems. So as far as I know, this problem in momentum space was like wide open. And unless somebody interrupts me right now, I'm going to still assume that it was open. So yeah.
Are you going to describe these cells in these forms?
Yes, I'm going to describe the cells, or at least some kind of. I'm not going to describe the cells, but I'm going to give some origami interpretation of the cells. Okay. Any other questions? Okay. Yeah, let me try to explain this theorem. So far, I only explained the Mandelstam positive region. let me try to explain all the other words in the theorem. So here's the Mandelstam positive region again. And first of all, what is BCFW? So BCFW is 4 people. That's Brito, Cachazo, Feng, and Witten. And so they found this recurrence for the amplitude. Previously, you had to compute the amplitude using some kind of Feynman diagrams, which there's a lot of them, and they give you complicated expressions. But once you apply BCFW, it gives you fewer terms, and each term is nicer, I guess. So it's a finite sum where each term is labeled by, the terms are labeled by planar bipartite graphs in a disk. So this collection of planar bipartite graphs is defined for each k and n in a recursive way. So what you do is you want to build a graph. You start with n external legs, which are your particles, and you fix 2 adjacent external legs. So here I fixed 1 and 2, and you put a little bridge. There's going to be a little bridge, and then this area is going to be completely fixed by throughout the recurrence. Just this part is fixed, and then I look for all possible ways to split the rest of the picture into 2 blobs. So I go through all possible indices j, and then I want to split it into 2 parts. And then I continue recursively. So let's say I take the blob on the left. I choose 2 adjacent external legs. I put a little bridge here. And then I look for all ways to split the left guy. And similarly for the right guy until I get an honest planar bipartite graph. So that's roughly how the recurrence works. And notice that these planar bipartite graphs are natural planar duals of origami crease patterns. Right? An origami crease pattern, all faces are colored black or white in a bipartite way. So if you just take the planar dual, you get a planar bipartite graph in a disk. And of course, the origami crease pattern was geometrically embedded in the plane. And these planar bipartite graphs are kind of abstract planar graphs. You know, they fix the boundary, cyclic boundary ordering, but you don't fix any particular embedding in the plane. Okay. So I'm going to return to this picture a bit later. For now, let me try to reformulate so if you apply the main result to this theorem, I guess I'm not going to explain what the BCFW cells are, but if you reformulate it in the origami language, then you get the following statement, which I think has all the words familiar to you. So the claim is that basically, so you have this region here, the Mandelstam positive region, which kind of looks, it's some kind of high-dimensional region. And so the claim is that it's going to be triangulated. It's going to be subdivided into pieces labeled by these BCFW planar bipartite graphs. And so the claim is that if you pick any generic point, so you just kind of throw your darts at the blackboard, you pick some generic point, lambda, lambda tilde. And the claim is that, first of all, there's going to be a unique cell that this point belongs to. So there's going to be a unique gamma, this planar bipartite graph. And second of all, each piece is going to map injectively, which by definition means that there's a unique origami crease pattern whose 4-dimensional boundary is given by lambda, lambda tilde, and whose planar dual graph is gamma. So these BCFW pieces in the kinematic space, they are basically, for each graph, you look for all possible origami crease patterns with given combinatorics. Right? The dual graph describes the combinatorics, but not the geometry of the origami crease pattern. So you fix the combinatorics, you look for all possible origami crease patterns, and you look at their boundaries, and that's the subset of lambda, lambda tilde that you're going to get. And for people more familiar with the usual Amplituhedran story, usually there is 3 conditions. One is injectivity, which means that every piece maps injectively. And so in this theorem, this appears as the condition that the origami crease pattern has to be unique. There's disjointness, that any two cells in this picture are disjoint from each other, like the interiors of cells are disjoint. And this corresponds to gamma being unique. And finally, there is surjectivity, that there is no holes in this picture. right? That the different pieces cover the entire Mandelstam positive region without any holes. And that is mentioned here because for each generic point, there is some piece that covers it. Okay.
Are you picking out some special way of running BCFW here, or no?
No. Well, I mean, for any way to run the BCFW, right? I made some choice, like in the BCFW recurrence, I made a choice.
Always like shifting and then one.
No. Any way to run the BCFW recurrence is going to work. Yeah, there is like two separate open problems here. Yeah, so here I chose these two particular external legs, and then I chose to have a white vertex on the right and a black vertex on the left. Like I could have flipped this choice, but I have to do it in advance for at this level, but then for each individual half, I can choose some other way to run the recurrence. Yeah. What exactly what for non-BCFW? Well, for each cell, basically, I mean, you can choose any planar bipartite graph and look for all origami crease patterns. And so you're going to get some kind of subregion here, which I mean, and it could be that for each point there is like lots of origami crease patterns with this boundary. If you choose a non-BCFW cell, then the pieces are not going to map injectively, right? There could be they could be higher dimensional, so there could be some loss of information. And so the theorem here is that if you choose the BCFW pieces, then they correctly triangulate this region. Any other questions?
There are collections of cells that tile the Amplituhedra that you don't actually see from any particular way of running the recurrence. Do you see those guys too, or?
I don't immediately see them. I mean, you can define them and you can ask, do these particular cells triangulate? And maybe you can prove it in the same way as I did, and maybe not. It's the proof is specific to the BCFW recurrence. Any other questions? All right. So I'm gonna actually try to give you the proof. So it's to go from this theorem to this theorem, you have to apply the main result, which the proof is kind of long. But once you do this, then this theorem I can actually prove it to you. So here's the proof. You do this BCFW recurrence, and the first step is to prove injectivity, which by definition means that you fix a point in this region, and then you also fix, let's say you know the piece that this point belongs to. So lambda is known to you, and lambda tilde and gamma, all of these are known to you. So in other words, I know where I split, like I know where gamma was split. I know this index j here. And then I'm trying to recover the origami crease pattern from this input. And what do I know already? First of all, lambda and lambda tilde tells me this boundary polygon. Right? This boundary polygon only fully depends on lambda, lambda tilde. And the whole game is essentially to find this point V here. Once you found V, you can kind of recursively continue for the left and the right parts sort of independently. And so how do you find V? Well, first of all, lambda and lambda tilde tell you a little bit more. Right? They tell you not only the boundary, but also the origami folded boundary. Right? So they tell me the sum of black and white angles at each boundary vertex. And because I know that there's like one black vertex here and one white vertex here, I know that there's going to be a single black tile here and a single white tile here. And so I'm going to know these angles. So lambda and lambda tilde determine this red ray. And I know that V is going to be somewhere on this ray. I don't know where it's going to be, but I know V has to be on this ray. And then how do I find it, where it is on this ray? Well, I notice that since gamma is given to me, I know this vertex U sub j. So the boundary vertex U sub j is known to me, and I know that this edge here is an edge of the origami crease pattern. So I know that my origami map is gonna be an isometry on this edge. Okay, and so the origami map is defined after shift and rotation. So I can shift and rotate it in such a way that it fixes the white triangle. Basically, before folding the origami, I kind of nail this white triangle to the table, and then I fold everything else on top of it. So the origami map is going to fix the white triangle, and in particular, it's going to fix this array rho. And so then the origami map is going to send this vertex somewhere else, but V has to be at equal distance from U sub j and from its origami image, because the origami map is an isometry. Does it make sense? Or yeah, so I know that this is an edge, so I know that V has to be at the same distance from this boundary point and its image, all of which are determined by lambda. So I recover V as the intersection of the perpendicular bisector with the ray. And that's really how you recover V, and then you recover everything else recursively. Okay. And yeah, so that's a very geometric way to prove injectivity. And once you work out all the formulas for these complex numbers, intersection of the perpendicular bisector with the ray, et cetera, the formula becomes very easy. And this, again, may be obvious in retrospect. So the formula is not only kind of very simple, but also it already appears in the original BCFW paper, which was doing something different. Like they were doing complex analysis. You deform the amplitude, and then you look for all these poles, and then you sum up the residues. And it turns out that the formula for the poles is exactly the same as the formula for this vertex V here. So what is happening here? You start with, you want to deform the amplitude. So you pick this 4-dimensional vector Q, which corresponds to lambda1 and lambda2 tilde, and it essentially encodes this ray. So Q encodes this ray here, and the only question is how far do I want to go along this ray? And the condition is that this vector, like the difference between V and Uj, has to have squared norm equal to 0. So this expression has to have squared norm equal to 0, and Q itself squares to 0. So this is a linear equation on T. You solve it, and you get this formula here. So you have the Mandelstam variable in the numerator, and you've got some kind of Minkowski scalar product in the denominator. Okay. And so that's exactly the same formula as you get from the perpendicular bisector story. Any questions on this? All right. Yeah, go ahead. On the boundary, you mean between two regions? Well, actually, I mean, I guess something becomes, if you go to external boundary, then I mean, your perpendicular bisector could become parallel to the ray. There could be some kind of edge cases like this. If you look at an internal boundary, then I'm going to tell you what happens in a second. There's some other things. Yeah? Great, yeah, great question. So where does the positivity of Mandelstam variable come in? So far, it hasn't come in. So this works. I mean, this procedure works for any lambda tilde and any gamma. That's BCFW, any BCFW graph gamma. But now let me prove the second part, which is that the cells are disjoint. We want to, in other words, I no longer tell you where I split the graph. Right? I don't tell you gamma. I only tell you lambda tilde. So how do I recover gamma? By just looking at the boundary data. And what turns out to work is that you basically you try to split it in all possible ways. So for each index j here, you compute this quantity, and which tells you how far do you want to go along this array. Right? The array itself is fixed by lambda tilde. And then you choose the closest point to the boundary. You choose the minimal possible positive value that this quantity can have, can be. And this only works assuming Mandelstam positivity. So in other words, somewhere along the way, I have to use the fact that the numerator of this expression has to be positive. And so in particular, here I say generic. What it means to be generic is that the minimum has to be achieved exactly once of this expression. And these little walls correspond to the minimum being achieved twice. Okay. And yeah, so that's the disjointness. And finally, these two steps give you an algorithm. It's a reconstruction algorithm for any lambda lambda tilde. How do you recover the origami crease pattern? And so there is a third step, which is to show that for any generic point in this picture, if you run the algorithm, you get a valid origami crease pattern. In particular, you have to check that for this vertex here that the sum of white angles has to be equal to the sum of black angles. And then you have to check that the entire picture is embedded in the plane. There is no weird self-intersections. Every face is a convex polygon, not self-intersecting, etc. So, but that's like a few pages of work, but basically, all the steps are essentially using the kind of planar Euclidean geometry, perpendicular bisectors, and all these things.
So the fact that this thing satisfies factorization, that's just that as you move things around, so one of the Mandelstam becomes 0, the point moves to the boundary, and you just split the crease pattern in two.
Yeah, the factorization channels, they correspond to when your origami crease pattern has an edge like this, and this edge is, it's an isometry on this edge, so this edge is going to have the same length after origami, and so that corresponds to the factorization. Yeah. So the
point moving
yeah. So it kind of that corresponds to, I guess that's one of the boundaries in this picture. Yeah, or to infinity or something like this. Yeah. But if you move v to this point here, yeah, then this edge precisely becomes like this.
So it's obvious that our factorization.
Yes, yeah, it is obvious. Thanks. Yeah. Any other questions? All right. That's the end of the proof of the BCFW recurrence. Let me try to go back to the original, to the main result. And I said that there is a simple bijection. Let me try to actually explain what this bijection is doing. So I've got I want to start with a triple lambda inside of C, inside of lambda tilde perp, where C is, a totally negative K plane. And I want to end up with an origami crease pattern. So first of all, I'm going to replace C, right? So there is this construction which is due to Postnikov called the boundary measurement map, which tells you that C, these totally non-negative K planes, are in bijection with weighted planar bipartite graphs in a disk. So here's an example. You have a planar bipartite graph in a disk. You put some kind of positive real numbers on the edges, and then you do the boundary measurements. So you run some kind of dimer. You take n choose k dimer model measurements with different boundary data, and so you get n choose k minors of some k by n matrix, and this is like a one-to-one correspondence modulo square moves or something like this. So that's the construction that's familiar to probably many of you, and I'm going to tell you an alternative construction that could be less familiar. So alternatively, instead of doing this, you start with a weighted planar bipartite graph in a disk, and then I claim that C, the matrix, the K plane C, is the space of all white holomorphic functions on gamma, where by definition a white holomorphic function is a function on the white vertices which satisfies a linear equation at each interior black vertex. And the coefficients are what is called the Castellane edge weights. So the coefficients are plus or minus usual edge weights. You sprinkle some signs into the edge weights so that there are some conditions. For any square, this product of signs is negative. For any hexagon, it's positive, negative for an octagon, etc. Anyways, there are some signs on the edge weights, and then once you introduce the signs, you basically C is just basically any white holomorphic function is going to be uniquely determined by its values on the boundary, and then C is just the collection of possible values on the boundary of white holomorphic functions. And similarly, dually, if you look for black holomorphic functions which are defined on black vertices, and for each interior white vertex satisfy the same kind of linear equation, then this describes the orthogonal complement of C. So if I start with a triple, like a two-plane lambda inside of C and a two-plane lambda tilde, which is inside the orthogonal complement of C, then I'm going to end up with a pair of a white holomorphic function with values in R2 and a black holomorphic function with values in R2. And so I switch from R2 to C again. And I get a pair of complex valued white and black holomorphic functions on the same weighted planar bipartite graph. So the final step is to how do you recover the origami crease pattern from this data. And this construction is what I call the Kenyon-Smirnov primitive. Basically, I mean, to define the origami map, to define the origami crease pattern, you want to associate a complex number to each face of your graph gamma. And the way you do the rule is that for any edge of your graph gamma, the dual edge, the difference here is going to be just the product of the Castellane edge weight times the value of the white holomorphic function times the value of the black holomorphic function. So this is a complex number for each edge. And then you can check, like why, if you go around any black vertex and you sum up the differences, you're going to get 0 because why? Yeah, it's a question for the audience. Why is this consistent as you go around any black or white vertex? You can just yell it out. I can wait. I don't mind.
Momentum conservation?
Momentum conservation. So the momentum conservation is defined on the boundary, right? But then you want this to be, so somehow the momentum conservation, you're correct that it is like, if you think of this picture as just the entire origami crease pattern, then this is like momentum conservation. But then why does momentum conservation hold for each one of these little vertices? Which angle? Oh yeah, sum of angles. Yeah, that's not really so far visible in the, not it's. All right. I mean, the answer is just because of this equation here. If you go around the black vertex, then the value of the black holomorphic function is fixed. And so you sum up these expressions here, which by definition are 0. So the sum of differences is 0, and similarly, if you go around any white vertex, the sum of differences is 0 because lambda tilde is a black holomorphic function. Okay, is this clear or? Okay, yeah. This kind of, the fact that this is consistent is a very simple consequence of the white holomorphicity and the black holomorphicity.
Wow, this is reverse engineering how the connection between the amplitude and the Grassmann came about.
Yeah. So if you look at it in the book by Nima and Jara and Jake and Alex and a bunch of other people, the way they do this is they have a little Grassmannian for each black vertex and a little Grassmannian for each white vertex, and then they glue things together. In precisely sort of this way. They have a linear equation for each black vertex and a linear equation for each white vertex. So yeah, it's all kind of reverse engineering, but yeah, this construction is actually appeared in the dimer model story a little bit before the book. So yeah, first of all, this Kenyon did this for the dimer model on the squared lattice, and then Smirnov used it for the conformal invariance of the Ising model, and then it was generalized in these papers. So this construction here is really from these two papers, and yeah. So and the angle condition that first of all, the origami map is very nicely just obtained by you take the complex conjugate of the white holomorphic. Yeah, go ahead.
Sorry, I missed this one. How does this lambda suddenly become a function on the vertex in the graph?
Right. So yeah, so any white holomorphic function is uniquely defined by its boundary values. So originally lambda was a two-plane, right? So it was kind of, you only knew the values on the boundary. And then the claim is that once you know the values on the boundary, you can uniquely propagate them inside. Yeah. So this equation, I mean, it's a linear system of equations. Claim is you can solve it with a unique solution. Any other questions? Okay. Yeah, so the claim is that the origami map is also very easy to write down. You just conjugate the white holomorphic function, and that corresponds to like flipping all the black triangles and keeping all the white triangles orientation. And yeah, and in particular, so what is easy? An easy consequence of this construction for any white holomorphic lambda and black holomorphic lambda tilde is that the angle condition is always going to be satisfied modulo 2 pi. So the sum of angles at each interior vertex here could be pi or 3 pi or negative pi. And it's completely unclear why the result could be non-self-intersecting in any way, because like you can obtain, this is the equation for the bird, right? So this is the origami crease pattern, and then this is what happens after you fold it. So definitely no self-intersections could appear because the bird is very self-intersecting. But so the hard part is to show that if your initial data, lambda, lambda tilde, satisfy those Weinstein number conditions and positivity conditions, then you're guaranteed to have an embedded pattern in the plane. And every face is going to be an honest convex polygon. The angle condition is going to be satisfied not just modulo 2 pi, but just actually the sum of angles is going to be equal to pi, and etc. So I want to try to explain what sort of ingredients go into this proof. And yeah, so here's the theorem again. And the main part of the proof, like the main ingredient of the proof, is really the so-called magic projector, which was introduced in this paper for the coordinate transformation from momentum space to the momentum twistor space. So it's familiar to some of you. And they say it works like magic, so I call it the magic projector. And so here's the definition. It's a linear map from Rn to itself, whose kernel is lambda, the two-plane here. And the formula, if C has columns Ci, then the formula for this guy is expressed in terms of these 2x2 minors of lambda using basically Cramer's rule. Okay? So if you plug in lambda into this expression, you're going to get 0. If you plug in any k-plane C which contains lambda, you're going to get a k-2 plane. And so sort of you have this operator. And so they use the Jacobian works out very nicely. The amplitude, you can rewrite it. You can observe dual conformal symmetry, all that stuff. And basically, there's a result which I proved, which was anticipated ever since this paper, I think, which is that if lambda has the correct Weinstein number and the correct positivity conditions, then this operator preserves total positivity. So if you start with a k-plane that's totally non-negative and contains lambda, you apply this operator, then the claim is that you still get a totally non-negative k-2 plane. Yeah, so this was even stated in some papers as a theorem, but yeah, I don't think nobody proved it. And you can prove it using some kind of topological argument. So some connected components, blah, blah, blah. And it's a little tricky because you have to show that the set of pairs lambda inside of C is connected, and that turns out to be not exactly obvious. But yeah, the claim is that once you prove this result, this magic projector happens to control origami crease patterns. And so the claim is that once you prove this, then as a corollary, you get that indeed your origami crease pattern is going to be valid. And what goes into, to go from the proposition to the corollary, there is a different idea that I'd like to briefly explain. So there's this construction which I call shift by 2, and then some of you are familiar with this under the name T-duality. So you start with a planar bipartite graph in a disk, and then you insert some degree 2 white vertices to make every black vertex trivalent. And then you draw a little black or dark triangle around each black face, and you triangulate the white regions so you have like a triangulation of a disk into dark and white regions. And then you apply T-duality twice. So what you do is for each white triangle, you insert inside of each white triangle, you put a trivalent white vertex. and then with like 3 black vertices. And so you get another planar bipartite graph in the disk, which I call the shift by 2 of gamma. And yeah, so this construction, yeah, originally it actually appeared in my paper on like matroids and zonotopal tilings and Plavy graphs, but then it was later generalized and streamlined, and eventually it was applied to the amplituhedron because it has like the correct effect on the strand permutation of the graph. We shift the strand permutation, so yeah, it is related to the BCFW shift. And so this construction is kind of by this point well known, but it's only known at the combinatorial level. So in other words, if I have a weighted planar bipartite graph, then I don't really know how to transfer the weights from the graph to the shifted graph. And yeah, so this has been bugging me for like a few years. Like, what is the canonical weight transformation? And it turns out that there is no canonical way to do this, but instead, if you so the weighted graph just corresponds to k-plane C, right? That's the boundary measurement map. But if you fix a 2-plane lambda inside of C, then there's a very nice canonical weight transformation that I'm going to explain now. So you start with a 2-plane lambda inside of C, k-plane C, and you can extend them to white holomorphic functions on the white vertices of gamma, as before. And the claim is that now, once you know the extension of lambda to the white vertices, then you can forget the edge weights. Right? You know lambda is white holomorphic, so you know that it satisfies, like at each black vertex, it satisfies a linear equation. Like the values at the 3 white vertices satisfy a linear equation. And the coefficients of that linear equation, because these are vectors in the plane, there's a unique linear equation. So the coefficients are just these determinants, these local little determinants inside of each triangle. And so that's how you transfer the edge weights. You just take this determinant here, inside of each black triangle here, and you do the same. You use the same determinants for each white triangle here. And so you get another shifted, weighted, planar bipartite graph. And you can even transfer C. So C was another white holomorphic function with values in RWK, which sort of contains lambda. And so if you, for each white triangle, you want to apply like a Q projector locally. So you have 3 vertices, W1, W2, W3. Here you're going to have a single white vertex inside. And so the value at the white vertex inside is basically Kramer's rule in the original white triangle. So if you plug in lambda into this formula, you're going to get 0. And so you get a k minus 2-dimensional white holomorphic function on the right. And the claim is that this white holomorphic function is the unique white holomorphic extension of C times Q lambda. So I don't know how clear this was, but to sum up, you want this projector Q lambda, it acts on the boundary. So the columns of C are written on the boundary of the graph. When you act by Q, you get values on the boundary of this graph. But then this rule here lets you propagate the action of Q from the boundary into the interior in like a unique way. And so separately, we know that this guy is totally non-negative by a topological argument. And because it's totally non-negative, it controls the signs of these edge weights. It controls the edge weights, which are these determinants here. And so because it controls the signs, you can these determinants are literally they control the orientation of the black and white, of black triangles in the origami crease pattern. So this is how you show that all the black triangles are correctly oriented. And then if you replace lambda with lambda tilde, you show that all white triangles are correctly oriented. And that's it. That's sort of the end of the proof. There's some work that goes into these implications, but that's the gist of the proof. Any questions on this? Okay.
The integral map normally connects this Amplituhedran momentum space to the momentum picture space. So somehow you used it so importantly. So why isn't the whole story run in momentum picture?
Why isn't the whole story run in momentum twistor? Yeah, I mean, the origami crease patterns naturally live in momentum space. Yeah.
To prove something about the crease pattern being correct, you still have to do this the P-dwelling map, and I assume that the edge weights downstairs can be thought of as some of the components of the momentum.
Right. Yeah. So the things downstairs, they control the orientations of black triangles on top, but yeah, somehow you can just yeah. So the origami crease pattern itself is on top, and then these orientations are downstairs, and then like if you just focus on the downstairs, there is no origami crease pattern. You can't really say anything about the original. Yeah, like all these perpendicular bisectors, they live in the on top. You can't really, at least I don't immediately see how to transfer them downstairs. Any other questions? Okay, I've got 2 more slides, and then I'm going to be done. So first of all, I haven't mentioned the amplituhedron yet. So the main theorem is about triangulations of the momentum amplituhedron, which was introduced by Damgard, Ferro, Lukovsky, Parisi. So let me very briefly mention what this object is. If you're familiar with the usual amplituhedron, there you start with a positive matrix Z. Here you start with a pair, so a positive k minus 2 plane lambda tilde, positive k minus 2 plane lambda perp, and positive k plus 2 plane lambda tilde. And the momentum amplituhedron map, by definition, is the intersection map. So you start with a k plane C, and then you intersect it with capital lambda, or you take the orthogonal complement and intersect with lambda tilde. So the claim is that you get a pair of 2 planes which belong to this positive kinematic space here. Okay, so each plane is 2-dimensional. They're going to be orthogonal to each other because one is in C, another one is C perp, and all the winding number conditions are also going to be satisfied kind of automatically. And so the momentum amplituhedron, by definition, is this image of the totally non-negative Grassmannian under this momentum amplituhedron map. And the hope, I think, of the authors was that the Mandelstam variables would always be non-negative on this. Like this would be the positive geometry for the amplitude. And the answer is that sometimes the Mandelstam variables they say that like on a very small region of the momentum amplituhedron, some Mandelstam variables become negative. And they had some conjectures for like when lambda perp and lambda tilde are van der Monde, then this guarantees that the Mandelstam variables are positive. And I was kind of skeptical about this, but eventually I proved it. So here's a more general result. If you don't choose them independently, right? Lambda perp and lambda tilde, you choose them so that lambda perp is inside lambda tilde. And moreover, there's some positive flag variety condition that basically, so this guy is k minus 2-dimensional, this guy is k plus 2-dimensional, and you want there to be a flag of subspaces. So k minus 2, k minus 1, k plus 1, k plus 2, and you want all of them to be totally non-negative. Once this is true, then every point of I call it the flag momentum amplituhedron, every point of the flag momentum amplituhedron is going to be Mandelstam positive or non-negative. Yeah. And the reason I care about this is because, as I mentioned, so Mandelstam variables, they tell you about the origami crease patterns. Like, and in particular, you can show that if all of these are non-negative, then the origami crease pattern is not going to have self-intersections. So I showed you some picture where it's there's a slight overlap. And once you guarantee that these are non-negative, then there's going to be no overlap. You're going to get an honest region homeomorphic to a disk. And in particular, this solves another, so one big application is the BCFW triangulations conjecture. Another big application is this open problem from analysis or statistical mechanics that these people have been working on. Essentially, that for any weighted planar bipartite graph in a disk, you can realize it using an origami crease pattern with edge weights gauge equivalent to the original one. So gauge equivalence means you rescale the edge weights at each vertex. It doesn't really matter. It's some action that preserves the dimer model. And so what these people like to do is they can do analysis on the origami crease patterns. Right? They're trying to take sequences of graphs which approximate some region, and then they're trying to show that some functions are conformally invariant. Some functions that come from the dimer model are conformally invariant. And they can do this for origami crease patterns, but they couldn't prove that the origami crease patterns exist. Outside of a few special cases, you want to show existence, and for any kind of bipartite graph with edge weights given in advance. And so that was their problem. And then so it becomes a very simple corollary of this amplituhedron story with if you apply the bijection with origami crease patterns. And so this is all very nice and natural. Let me try to end with something completely weird and unnatural. So here's the last slide, Varchenko's conjecture. So if you take a different problem, right, you're given a weighted graph and you want to count origami crease patterns with fixed two-dimensional boundary. So in this case, I chose the boundary to be this like house-shaped region, and then I chose some graph. So here are all of these are gauge equivalent edge weights to each other. So question is, how many solutions do you get? And in this case, you get exactly 5 solutions. So there's no more origami crease patterns with this particular boundary. And the answer in general turns out to be that the number of solutions is the number of bounded regions of a positroid hyperplane arrangement, which I don't think people have studied before, but it's a very simple thing. So you take the boundary measurement map, which is going to be some k by n matrix, and then you just look at the hyperplanes which are orthogonal to the column vectors. Right? You take these hyperplanes, and I mean, I'm going to do something a little different because I want affine hyperplanes. So I make the first column to be like the basis vector 1, 0, 0, 0. And then I just use the rest of the top row as my constant terms, and these things here as coefficients of my hyperplanes. So like this hyperplane 7x plus 2y equals 6 corresponds to this column vector here, 7 to minus 6. So you do this for all these columns, and then you get a bunch of hyperplanes, and then you count the bounded regions. Okay, so compact regions in the complement of these hyperplanes. And here you have like 1, 2, 3, 4, and 5. So there is 5 bounded regions, and somehow they correspond to the 5 origami crease patterns. And in general, some of these may be kind of folded, so they are not always non-self-intersecting. So in general, this number is greater or equal than this number. But yeah, the proof is basically that once you rewrite this in a certain way, these solutions are in bijection with critical points of Varchenko's master function, which is some kind of product. It's a product of these linear functions raised to some generic powers. So, and Varchenko showed that each bounded region has a unique critical point in some kind of favorable circumstances. And then Orlik and Terrell proved his conjecture more generally for any hyperplane arrangement using cohomology of complements of hyperplane arrangements. And so the reason I mentioned this is because there is a recent paper by Thomas which connects Varchenko's master functions to these CHY scattering equations, which some of you physicists know about. So each of them is some kind of sum over solutions, and then Thomas showed that these solutions correspond to critical points of some Varchenko master function. So that's really that's a weird connection. I don't know what to do with this. If you know, please tell me. And that's it. Thank you very much.
Thanks so much, Pasha, for a wonderful talk. Are there any questions?
Maybe I'll start. On the previous slide where you had the flag right, the amplituhedron, what do you know about the canonical form? Can it be expressed nicely in terms of Mandelstam coordinates?
Yeah, so I don't so far. I tried the canonical form for a while and like do the origami crease patterns, give you any new information for how to write the canonical form, and so far I don't know. Yes, you can try to use the angles of these origami crease patterns as coordinates, and that maybe helps a little bit, but in general, I don't see any kind of beautiful statement there.
In the original momentum amplituhedron paper, didn't they conjecture that BCFW cells always give a tiling regardless of whether Mandelstam's are positive? And if so, do you believe that that's true?
Oh, so I don't know if they conjectured it. I tried looking for particular conjectures, and it's very hard because everything is claimed to be true. So, but yeah, I don't know if so. The question is whether if Mandelstam variables may be some of them are negative, do they still triangulate the space? And I don't know the answer. I think my computer tells me that the answer is probably no, but I don't know for sure. And but my proof at least doesn't work with negative.
So how important is the decomposition in terms of BCFW itself? Because we can also try to triangulate the amplituhedron using these sign flip patterns, which overlap with BCFW for simple cases, but in general, just look different. Do you think that for these sign flip regions, there might be something?
So I didn't fully hear you, but I think the answer is I don't know. Yeah, you have these other collections of cells which sometimes overlap with BCFW, sometimes not. Yeah, like the proof is very specific to BCFW. I haven't thought about any other collections of cells. Was that the question?
Yes. So there, in the definition, in the sign flip definition of the amplituhedron, you have different sign flip patterns that you kind of decompose it into. So it overlaps with BCFW for some simple cases, but in general, it might be a collection of BCFW cells or something. That it was not explored.
Yeah, I haven't thought about sign flips. That's a good question. I don't know.
Simple question. So the whole story begins with these two polygons, which, as you say, we can think of as the four-dimensional space broken into the space part and the time part. There's a polygon for each from momentum conservation, and the sort of magic is that the magnitudes are equal under the origami method. Wonderful. But that picture obscures the full four-dimensional Lorentz invariance that mixes up the space and the time components. What is the action of that full SL2 cross SL2 or SL4?
Yeah. Right. So if you apply these sort of operations to lambda lambda tilde, I have no idea. So the origami crease pattern changes a lot, and I don't know how to predict how it changes.
Cross U1, sort of obviously, but
Once symmetries, I don't really see. There's the dual conformal invariance is kind of, you can like this inversion map, because my origami crease patterns, I have actual vertices, so you can apply inversion, and you can kind of show that it preserves in a way these origami crease patterns, but the Lorentz invariance, I don't really know how to say anything.
You mod out and so on. So, but where did that? So I thought that meant that you understood the action of the
Yeah, so it means that you take an origami crease pattern, you apply these all Lorentz transformations, so you get lots and lots of origami crease patterns, and they all correspond to the same. Like you can.
That fact is not manifest.
Yeah, it's not manifest. Yeah, so you can extract lambda lambda tilde and see that they're the same, but you can't really without that. If I just show you two origami crease patterns, I can tell you if like the bird is Lorentz equivalent to somebody else.
What this might look like for the loop amplituhedron?
No. Yeah.
To begin with, just the origami level question seems pretty natural. Take the punctured plane and origami that.
Because the origami crease patterns, they can be for very non-reduced graphs. You can still look at there's loops correspond naturally to some kind of geometric patterns in the origami crease pattern. So yeah, that's.
I mean, just in your story, because there's still, I think, some confusion about what the loop momentum amplituhedron should be. I mean, there's some definitions. I don't think they're supernatural. But anyway, but you could do something very natural, like just take non-reduced graphs and run exactly the same story.
Yeah, and I haven't tried. Yeah, there's a bunch of things I haven't tried, and this one seems important. But yeah, I was trying to get the paper out before this today. So yeah.
Any other questions?
So there's a parallel story in 3 dimensions. If you sort of identify lambda and lambda tilde, and also change the Grassmannian to orthogonal Grassmannian, there should be something like a momentum amplitude in the so-called ABGM theory. Have you thought about, is there any natural extension of your story to have this?
Yeah, there is. Yeah. So for ABGM story, you can take these planar bipartite graphs to have some kind of symmetry, and that corresponds to the Ising model application of the totally non-negative Grassmannian. So I haven't thought about this too much, but I think it's going to work. Yeah, everything is going to work out. Like,
pattern and the original one have to look the same or something, because lambda equals lambda tilde in this picture.
Right.
well, they're lambda equals lambda tilde, but so the origami crease pattern is given by this formula here, which lambda. So you conjugate lambda, but and yeah. So I haven't. Yeah, I should try because yeah, I don't really know what happens. Lambda equals lambda tilde, C equals its own orthogonal complement, and the graphs are very nice. But yeah, so it's I could bet that it's going to work out, but yeah, I haven't tried.
So when the number of origami crease patterns is equal to the number of boundary regions?
No. So the question is, when is this an equality? And I don't know in general. So because yeah, for this to be an equality, you have to guarantee that the solution belongs to this positive kinematic space. And yeah, I couldn't. I was trying to find any conditions, but I couldn't. And experimentally, a lot of times, so I have some conjectures. Like if the boundary is a regular n-gon, then I conjecture that all solutions are going to be embedded and valid origami crease patterns. But in general, it seems hard to, like, sometimes there's, yeah, it depends on the boundary. Like if you choose the boundary to be self-intersecting, then the answer is 0. So like you still get this many solutions and none of them are going to correspond to crease patterns. And so if it's in between, then the answer is going to be in between.
I was just going to say for the m equals 1 amplituhedron, this can be identified with the bounded region of the cyclic arrangement. And then the different individual regions correspond to tiles and a tiling. So it feels somehow very related.
Oh yeah, but this, yeah, that's interesting. So yeah, and so those, I mean, you take the cyclic hyperplane arrangement, which I'm assuming corresponds to the particular positroid cell. Do you ever get positroid cells like lower positroid cells?
The Z matrix, or and so it's like the totally positive version. There have been extensions of that studied by Yelena Mandelstam and Lizzie's there. Sorry,
I'm here, Lizzie's there.
and Lizzie Pratt.
Well, Dimitri, who's not here.
Okay.
For a non-cyclic hyperplane arrangement, if it's a tame Grotz-Tope, then it's also the number of bounded regions of the arrangement.
Yeah, I've seen the paper, but I haven't thought about this connection. Cool. I don't know.
But in your setup, the origami crease patterns are like tile.
Well, yeah, the combinatorics. Well, no, I mean, I don't. Maybe I didn't understand the question. So, what do you mean they are like tiles?
It was one case, the different bounded regions.
Right. They're tiles of the amplitude. Yeah, this is nothing like that, I think, because here the bounded regions correspond to just these different 5 pictures, which all have the same combinatorics. So yeah, I think it's possibly kind of orthogonal to situation. I don't. Yeah.
Any other questions for Pasha? All right, we're gonna come back for a Mishi at 11:45, since we started a few minutes late. But let's thank Pasha again for a really wonderful talk.